Hello, welcome to this lecture video. So we are going to talk about Hermitian matrices. So it is a special class of matrices. So I am teacher Melay. So let us start by giving the definition of Hermitian matrix. So a square complex matrix A is called Hermitian if A raised to H is equal to A. Equivalently, if the conjugate of matrix A is equal to the transpose of matrix A. So by this definition, we know that a possible Hermitian matrix is that when it is a square complex matrix A. So just to recall, a square matrix is when we have, of course, the same number of columns and the same number of rows, or if for example, as mentioned in the previous videos, we can denote our matrix as, or the order is m times n. So which means the value of the number of m or the number of row is equal to the number of columns. So m is equal to n. Okay, while in our also previous discussion, we made mention that a matrix can contain real numbers, it can contain functions, variables. And so in the case of this example, or in this type of special classes of matrices, so this is a complex matrix. So I would just like to highlight that possible Hermitian are those matrices that are square complex matrix A. So how will we know that this is Hermitian matrices? So we have a symbol for, so as mentioned, this is the conjugate of matrix A with a line above, and it is, or bar above, and we have, of course, the transpose of matrix A. So we have to check the transpose and its conjugate. Okay, so there are also ways for us to determine if it is Hermitian matrices by observation. So if we observe, for example, that the entries on the main diagonals are real, or it is real numbers, and that the reflection of each non-diagonal entry in the main diagonals are conjugate of that entry. So we can also determine that this is Hermitian matrices. But for you to make sure that it is Hermitian matrices, then you can get its transpose and its conjugate. So before coming up with an example of Hermitian matrices, there is a need for us to review what is a conjugate of a matrix. So as mentioned, it is a conjugate. We can actually use, or we can get a conjugate of a complex matrix by considering now that the entry, we will get the inverse operation of each of the entry. And the policy, or rather the rule there, is that the conjugate of a matrix, a complex element, is its inverse operation. So if it is addition, it will become subtraction. While if it is subtraction, it becomes addition. While if of course, it contains a real number, the real number will be retained, or it will remain unchanged. And this is already mentioned in our previous slide. It can be denoted as A with bar above. So just to show you the conjugate of a matrix, so let us have an example of this. So let's see. So for example, we have A is equal to, so let us consider an example for this. It is equal to, let's say we have 4i minus 2. We have 2i. Let us say we have here 8, 2 minus I, 4 I, 7, 3, and 5. So this is a complex matrix. It contains complex numbers and real numbers. So as mentioned, if we have complex numbers or complex elements here, so I, 2I, 4I, 2 minus I. The conjugate of this is its inverse operation, only for its complex elements. So example, for I minus 2, this is similar to the operation for I. We are referring to the operation of I. So it is a plus I minus 2. So this is the same as plus I minus 2. So this becomes, its conjugate is negative I minus 2. Or it can be written as negative 2 minus I. So it doesn't matter. So for 2I, the conjugate of 2I, so let's not place an equal sign here because of course it doesn't mean that it is equal. It is the conjugate. So the conjugate of 2I is negative 2I. So these are, as mentioned, the conjugates. Okay, next. 2 minus I. So the conjugate of 2 minus I is 2 plus I. So if you notice, we are not changing the operation of real numbers, only the complex number. And then for 4I, this is negative 4I. Therefore, if we will get the conjugate of A, this is equal to, so as mentioned, we will not change real numbers. So 4 will retain as 4. And then I minus 2 is negative I minus 2. 2I is negative 2I. 2 minus I is 2 plus I. Retain 8. 4I is negative 4I. And then retain 5, 7, and 3. So this is the conjugate of matrix A. So we remain or we retain the real numbers as is, and we just change the operation of the imaginary numbers. So the inverse operation of addition is subtraction, and the inverse operation of subtraction is addition. Okay, so let us go back to our slide. Okay, so now as mentioned, we have of course also the transpose. So let's go back there. So transpose of matrix A. So let's clear this. So what is a transpose of matrix A? So let's have another example. So just to review, if this is, let's say, okay, so if this is A, the transpose is, we will just swap the elements in our columns and our rows. So this will become elements of our column, and this will become the elements of our row. So we have 5, 4, 3, I. So we will just reverse its position. Or if not, you can also see it this way. So 5, 4 is now the new entry in the column, and 3I is the new entry in the second column. So the entries in the first row becomes the entries in the first column when it is transposed. Okay, so now let us try to determine whether this example is Hermitian matrix or not. So let us consider letter matrix A. So we have 5, 1 minus I, 8, 1 plus I, 7 I, 8 negative I, 6. So let us first get its transpose. So the transpose is, so we will interchange the entries in the rows and in the columns. So 5, 1 minus I, 8, 1 plus I, 7 I am already in the third row. So 8, negative I, and 6. Okay. So all the entries in the first row, 5, 1 minus I, 8, is now in my first column. All the entries in the second row is now in my second column. And all the entries in the third row is now in my third column. Now, what is the conjugate of A? So as mentioned, we will get the inverse operation if we have complex number. So we have 5. So this becomes 1 plus I because it is subtraction. So it becomes plus. So 8. So 1 plus I is 1 minus I. And then we have retain 7. I is negative I. 8. Negative I is, of course, positive I. So we can actually place plus sign if you like and retain 6. Now in our definition, if the conjugate is equal to its transpose, the conjugate of matrix A is equal to the transpose of matrix A, it is Hermitian matrix. So this is an example of Hermitian matrix because as you can see here, the corresponding entries of the transpose of A and the conjugate of A are all equal. Now in the given hint or some observations for you to determine whether it is Hermitian or not is that if the main diagonals are real numbers, so let us see. So we have 5, 7, 6, 8, 7, 8. So here, 5, 7, 6, 8, 7, 8. So diagonals are real numbers. So we have to check for that. But of course, we're not going to look at the transpose. So let's go back here. So what are the main diagonals? 5, 7, 6, 8, 7, 8. So the main diagonals are real numbers. Now, the reflection of non-diagonals are the conjugate or its conjugate. So the 1 plus I, its conjugate is 1 minus I. I, the conjugate is negative I. So it means even if we did not do the transpose and the conjugate, we can also determine whether our matrix is Hermitian by observation. But as mentioned, if you want to make sure that it is correct, then you can perform to see if the definition is, or rather to check if it's the conjugate of A and it's the transpose of A are equal. Okay, so let's have one more example. So let us also use set B. So for B, so let us just come up with what if it is not real numbers? I mean, what if the diagonal contains non-real numbers, so it is complex. So let's say, let's place negative I here. And then all the rest, so let's make it real numbers. And then after that, let us also consider, so let's say we have negative 2i here, positive 2i. Let's have 1 minus i, so 1 plus I. So by inspection, this is not a Hermitian because the diagonals contain complex number, and that is negative I. But just to check it, so let's do the checking. So let's get the conjugate of B. So what is the conjugate of B? So negative I becomes positive I. Negative 2i is 2i. Retain 3, and then 2i is negative 2i, retain 5. 1 minus I is 1 plus I, and then retain 1. 1 minus I, because this is 1 plus I, and 6. Now, let's get the transpose. So, negative I, negative 2i, 3. So, this is the entries in the first row. So, let us place the entries in the second row for our second column. 2i, 5, 1 minus I, and 1, 1 plus I, and 6. Okay, so as you can see here, we have the answer for conjugate of B is not the same with our answer for conjugate of transpose of matrix B because of this entry. So because here it is positive, and in our transpose it is negative. Okay, so that is how to determine whether our matrix square complex matrix is Hermitian or not. Okay, so this is all for this video. Thank you for watching.